Welcome to our course on structural analysis. This subject lies at the very heart of civil and structural engineering. Every bridge, building, tower, or highway that you see around you has gone through a process of structural analysis before it was built. The aim is simple: to make sure that the structure can carry the loads it will be subjected to, without collapsing, deforming excessively, or behaving unpredictably. Structural analysis is the systematic study of how loads are transferred through different elements of a structure and how those elements respond. As engineers, our job is to understand the forces, the moments, the displacements, and the stresses within a structure so that we can design safely and economically. In this first module, we will cover the foundations of structural analysis. We will begin by discussing the purpose and scope of the field, move into types of structures and supports, explore loads and loadings, and then proceed to the methods of analyzing statically determinate structures. We will also discuss equilibrium, internal forces, shear force and bending moment diagrams, and deflection of beams. By the end of this module, you will have a strong conceptual framework for understanding how structures behave under various conditions. 1. The purpose and scope of structural analysis. Structural analysis serves two major goals: safety and serviceability. Safety means that a structure should not collapse under expected loads. It should have sufficient strength and stability. Serviceability means that even if it does not collapse, the structure must not deform excessively, vibrate excessively, or crack in a way that prevents it from serving its purpose. Take for example a bridge. It must not only carry the weight of vehicles but must do so without deflecting so much that people feel unsafe while driving across. Similarly, a tall building must resist strong winds without swaying to the point where occupants feel uncomfortable. The scope of structural analysis includes determining internal forces such as axial force, shear force, and bending moment. Calculating deflections and rotations. Checking stability against collapse. Providing the necessary information for structural design. Thus, structural analysis forms the critical link between structural mechanics, which provides the theories, and structural design, which applies them in practice. 2. Types of structures. Structures come in many forms, and their classification helps us choose the right method of analysis. Beams, horizontal members that carry loads primarily by bending. Trusses, assemblies of straight members connected at joints, carrying loads mainly through axial tension and compression. Trusses are common in bridges and roof systems. Frames, combinations of beams and columns that carry bending, shear, and axial forces. Building skeletons are often frames. Arches, curved structures that carry loads mainly through compression. Cables and suspension bridges, flexible structures that resist loads by tension. Shells and plates, three-dimensional thin structures that resist loads through membrane stresses and bending. Each type of structure has its unique behavior. For example, trusses are designed so that members ideally carry only axial forces, whereas beams must resist significant bending moments. Recognizing the type of structure is the first step in analyzing it. 3. Types of supports and reactions. To analyze a structure, we must also understand how it is supported, because supports determine how forces flow through the structure. Pin support allows rotation but prevents translation in both directions. It provides two reaction components. Roller support allows rotation and translation in one direction but prevents translation in another. It provides one reaction. Fixed support restrains both translation and rotation. It provides three reactions in two-dimensional analysis. The choice of support affects whether the structure is statically determinate or indeterminate. A simply supported beam with a pin at one end and a roller at the other can be solved using equations of equilibrium. But if we replace one support with a fixed end, the structure becomes indeterminate, requiring more advanced methods. 4. Loads and loadings. Loads are the external forces applied to a structure. They can be classified as dead loads, permanent loads such as the self-weight of the structure and fixed equipment. Live loads, Variable loads such as people, furniture, or vehicles. Environmental loads, wind, snow, temperature changes, or earthquake forces. Dynamic loads, impact or vibration loads that change with time. Loads can act in different forms: concentrated point loads, uniformly distributed loads, varying loads, or even moment loads. For instance, the weight of cars on a bridge is considered a live load, while the weight of the concrete itself is a dead load. Engineers must consider the worst realistic combinations of loads to ensure safety. 5. Equilibrium of structures. The cornerstone of structural analysis is the principle of equilibrium. For a body to be stable, the sum of forces in each direction and the sum of moments about any point must be zero. This principle allows us to find the reactions at supports and, subsequently, the internal forces within the structure. For example, if a simply supported beam carries a uniform load, equilibrium equations allow us to calculate the vertical reactions at the supports before moving on to internal analysis. Equilibrium is not only mathematical but also conceptual. It ensures that every load applied is balanced by reactions, preventing the structure from moving uncontrollably. 6. Internal forces in structural members. When loads are applied to a structure, they induce internal forces in its members. These forces include axial force, tension or compression along the axis of the member; shear force, force that tends to slide one section relative to another; bending moment, a rotational effect that causes members to bend; torsion, twisting moment acting on a member. Understanding internal forces is crucial because they directly determine stresses and deflections in members. For example, a steel rod under tension experiences uniform axial stress, while a concrete beam under bending experiences compression at the top fibers and tension at the bottom. 7. Shear force and bending moment diagrams. One of the most fundamental topics in structural analysis is the construction of shear force diagrams, SFD, and bending moment diagrams, BMD. These diagrams show how shear and moment vary along the length of a beam. The steps typically involve calculating support reactions using equilibrium equations, cutting the beam at sections and analyzing internal forces, plotting shear force values to create the shear diagram, plotting bending moment values to create the moment diagram. These diagrams are powerful tools. The maximum shear force tells us where shear reinforcement may be needed. The maximum bending moment indicates the critical section for design. For example, a simply supported beam under a central point load will have maximum bending moment at the center and maximum shear at the supports. 8. Analysis of statically determined trusses. Trusses are analyzed using methods based on equilibrium, such as method of joints, solving for forces at each joint assuming all members are pin-connected; method of sections, cutting through the truss and analyzing a section to find forces in specific members. These methods help us determine whether each truss member is in tension or compression, which guides material choice and design. Trusses are efficient structures because members carry forces axially, allowing lightweight construction. However, proper analysis ensures that no member is overloaded. 9. Deflection of beams. Apart from internal forces, engineers must calculate how much a structure will deform under loads. Deflection is important because excessive movement can cause discomfort or even structural failure. Common methods of calculating beam deflections include the double integration method, the moment area method, the conjugate beam method, energy methods, such as Castellanos theorem. For example, a long-span floor beam might not break under load but could deflect so much that people walking across feel vibrations or instability. Thus, controlling deflections is as important as controlling stresses. 10. Introduction to statically indeterminate structures. So far, we have focused on statically determinate structures, where equilibrium equations are sufficient to solve for internal forces and reactions. However, in real life, many structures are statically indeterminate. This means there are more unknowns than equilibrium equations can handle. Examples include continuous beams, rigid frames, and fixed arches. In such cases, additional conditions like compatibility of deformations and material properties must be used. Advanced methods, such as slope deflection equations, moment distribution, or matrix analysis, are applied. We will explore these in greater detail in Module 2. Conclusion to Module 1. We have now laid a strong foundation for structural analysis. In this module, we explored the purpose and scope of the subject, types of structures and supports, loads and loading, principles of equilibrium, internal forces, shear force and bending moment diagrams, truss analysis, and beam deflections. This knowledge equips us to move toward more complex and realistic cases, where structures are not simply determinate but indeterminate. In the next module, we will tackle advanced topics, methods of analysis for indeterminate structures, matrix methods, influence lines, stability analysis, and modern computational approaches.